Good afternoon. In the video today, we will look at selected applications of trigonometry. The first is the AC series RL circuit. You can see that I have drawn this circuit here. We have a resistor and an inductor connected in series to the AC source. Now we're going to focus on opposition to current flow for this circuit. You know that the resistance is the opposition to current flow provided by the resistor. The inductive reactance, XL, is the opposition to current flow provided by the inductor. Now, the total opposition to current flow for the circuit is called the impedance, and it is the vector sum of these two quantities. Because it is the vector sum of the quantities are related according to a right triangle, with the impedance on the hypotenuse. The resistance and the inductive reactance form the legs of the triangle. And it's important to know that all three quantities are measured in ohms. So we can now solve these problems together. Let's read example 1. It says, in an AC series RL circuit, the inductive reactance is 35 ohms and the impedance is 48 ohms. We are asked to determine the resistance to the nearest hundredth. So let's go about solving that problem. Okay, so again, we're solving example 1. So what is it that we are provided with? We're provided with the inductive reactance. So that is XL, and it is 35 ohms. We are also given the impedance, which is Z. It is 48 ohms. What are we trying to find? The resistance. So it means we turn to our right triangle and we label 35 ohms here, 48 ohms here, and R here. So the three items are placed on the triangle, always with reference to this triangle. All right, you know that this is done with the Pythagorean theorem. We want to solve for R squared first, and we use subtraction because this is not the longest side of the triangle. So we want 48 squared minus 35 squared. So let's do that calculation. So 48 squared minus 35 squared is 1,079. And now we take the square root of that quantity to determine the resistance. There it is, and we want to round to the nearest hundredth. So to 2 decimal places, this will be 32.85. And the unit here is ohms. Okay, so that is example 1. So let's turn right away to the second example. It says, in an AC series RL circuit, the inductive reactance is 20 ohms and the resistance is 30 ohms. We want to determine the total impedance to the nearest hundredth. So the inductive reactance, this is XL, is 20 ohms. The resistance is 30 ohms. We're trying to determine the total impedance, and that is Z. So we begin by placing these quantities on the right triangle, again, with reference to this general triangle here. So what does this mean? We put 20 ohms here, 30 ohms here, and Z here. Using the Pythagorean theorem, this time we'll have adding, because we are finding that longest side length. So we want to do 30 squared plus 20 squared, or 20 squared plus 30 squared. Okay, so we get out our calculator now and we can punch that in. So we're doing 30 squared plus 20 squared. Okay, and so we get 1,300. And then we remember to take the square root of that. Now in problem 2, we are again rounding to the nearest hundredth. So in this case, that will be 36.06. And again, we include ohms as the final unit. So that's all there is to it. When you're solving for either resistance, inductive reactance, or impedance in a series RL circuit, you just have to effectively use the Pythagorean theorem. Okay, so now we're going to turn our attention to the next application, which is determining the sum of two vectors. In this case, they are voltages which are out of phase. Okay, so in the diagram here, we have on this side length the sum of the horizontal components of the voltages. And on this side length, we will have the sum of the vertical components of the voltages. And once we have those sums, we can use the Pythagorean theorem to find the resultant. And this is probably best explained by trying an example. So let's look at this first example. We have two voltages, E1 and E2, and they are applied to a resistor. E1 is 30 volts at 0 degrees reference. However, E2 is 50 volts and leads E1 by 35 degrees. So the voltages are not in phase. We have E2 leading by 35 degrees. And what we want to do is determine the resultant voltage to the nearest tenth. So let's begin to look at that problem. So this diagram explains the relationship between E1 and E2. So how did I draw this? It said E1 is 30 volts at 0 degrees. So I made this line 3 centimeters long to represent 30 volts, and it is at 0 degrees, which means it's just a horizontal vector pointing to the right, 0 degrees. And then I wanted E2, which is 50 volts, and leading by 35 degrees. So that means I turned up 35 degrees approximately. Okay, so I turned up this way, 35 degrees, and I drew a line 5 centimeters long. Okay, to represent 50 volts, and that's E2. So this is the relationship between them. So again, E1, 30 volts at 0 degrees, E2, 50 volts at 35 degrees. Okay, so now what I wanted to do was figure out what I'm using as the sum of the horizontal components and what I'm using as the sum of the vertical components. So I want to figure out EX and EY next. Okay. When it comes to E1 here, there is only a horizontal component. The horizontal component is equal to 30. The entire vector is horizontal. Okay, but when it comes to vector E2, take a look at this diagram. This shows vector E2. Again, it's 50 volts at 35 degrees. And I want to know for that vector, what is its horizontal component and what is its vertical component. So this is done by dropping a perpendicular here and making a right triangle. So we have 50 volts on the hypotenuse and 35 degrees here. This is the horizontal component of E2. So we're resolving the vector. How do we determine this side length? Well, quite simply, it is 50 times the cosine of 35 degrees. And how did I know that? Well, this side is adjacent to the angle. And remember, the cosine of 35 degrees is equal to the adjacent side divided by the hypotenuse. And so that means the adjacent side is 50 times the cosine of 35 degrees. And what about this side length here? Well, it is opposite the angle. So we would use sine. The sine of 35 degrees is equal to this side length divided by 50. So that means this side length is 50 times the sine of 35 degrees. So what are these values approximately? Well, we can work them out, right? Take out your calculator and let's just type in 50 cos 35. So that's 40.958-ish. Okay, I'm going to write that just here, 40.958. So that's this side length. It's close to 41 volts, right? These would certainly be volts. And what about this side length? We just do 50 sine 35. So it's 28.679, again, volts. So now we know that for the 50 volt vector at 35 degrees, its horizontal component is almost 41, and its vertical component is almost 29. So now we can write out our EX and our EY equations. So EX is the total of the horizontal components. So it's 30 cosine of 0 degrees plus 50 cosine of 35 degrees. And 30 cosine of 0 is just 30. And 50 cos 35 we already worked out. It's 40.958. So what we get is 70.958. Okay, and you can just type this in here to get this number all at once if you like. So 30 cos 0 plus 50 cos 35. So can you see that in the display right there? you'll get this answer, okay? So I tried to explain here how 50 volts is resolved into the horizontal component and the vertical component. But we can quite simply start from this picture and just use 30 cos 0 plus 50 cos 35 to get the total horizontal component here. And similarly, what would the vertical component be? Well, we can use 30 sine of 0 plus 50 sine of 35. Okay, so that's the quick, easy way to do it, just from the original picture. But 30 sine 0 will be 0, and that's what we wanted to happen because this vector has no vertical component. And 50 sine 35 we already worked out over here. Okay, so we get a total vertical component equal to 28.679, like that. Okay, so now we have the total horizontal component, that would be this side length, and the total vertical component, this would be this side length. So the very last step then is to find the resultant by using the Pythagorean theorem. And we are finding the longest side, so we will be using addition. So we're going to do 70.958 squared plus 28.679 squared, just like that. Okay, so I'm going to take out my calculator and do that calculation for you. I'm just going to raise this up a little bit. Okay, so 70.958 squared plus 28.679 squared is equal to this, 5,857.523. And then don't forget, we need to square root that to get our final answer. So without clearing your calculator, you just do square root equals, and there you have your answer. And we're rounding to the nearest tenth as per the instruction. So this would be 76.5 volts. Okay, so 76.5 volts is the result of adding these two original vectors. So E1 at 0 degrees added to E2 leading by 35 degrees gives you a sum equal to 76.5 volts. Okay, so that is the first example. And again, this is equal to 30 and this is equal to 0. And again, that's what you would expect because 30 is all horizontal and none of it is vertical. So this is 30, this is 0. Right here is the 40.958 and right here is the 28.679. Okay, we're going to do one more example because I know this is a little bit tricky maybe. So we're going to do one more example and it's virtually the same. So we're going to look here at example 2. So let's read it and then get started with our diagram. Okay, make sure I'm on the screen completely here. There we go. So, two voltages, E1 and E2, are applied to a resistor. E1 is 40 volts at 0 degrees. So I drew a horizontal line pointing to the right I made it 4 centimeters long and called that 40 volts. Okay? And then E2 is 25 volts and it leads by 65 degrees. So I turned up 65 degrees approximately, okay? And then drew a line 2.5 centimeters long to represent the 25 volts. So my scale is that I used, I said that every 1 centimeter was 10 volts, okay? So this is what we're trying to add. So we know that for this vector E1, 40 is the horizontal component and 0 is the vertical component. But for the other vector here, E2, we can work out the horizontal component and the vertical component if we look at this triangle. So here's the 25 volts inclined at 65 degrees, and then all I did was from the end of the vector, I dropped a perpendicular to make a right triangle. And now, again, this is the adjacent side. So the cosine of 65 degrees is adjacent over 25, and that means adjacent is 25 times the cosine of 65 degrees. And what is that equal to? 25 cos 65 is 10.565. So that's the length here. It's the shortest side in the triangle, and it is 10.565. Okay, so then what is the vertical component of this 25 volt vector? Well, this vertical side is opposite the angle. So we would use sine. The sine of 65 degrees would be the opposite side length divided by 25. That means the opposite side length is equal to 25 times the sine of 65 degrees. And so that is roughly 22.658. Okay, so now we have our horizontal and vertical components of that angle inclined at 65 degrees. So it's time to write out EX and EY. So EX is 40 cos 0 plus 40 plus 25 cos 65. Okay, so even if you don't draw this at all, you can write this out based on this picture. Okay, so 40 cos 0 plus 25 cos 65. All right, and so that's equal to 40 cos 0 is 40 plus 25 cos 65, we worked out here, it's 10.565. So what we get is a total horizontal component equal to 50.565. Okay, now what about EY? Well, all we do is we take cosine and change it to sine. So 40 sine 0 plus 25 sine 65. And this is 0 because this vector has no vertical component. And this 25 sine 65, we already worked out up here. It's 22.658. Okay, but again, if you don't want to draw this or work this out at all, you can just go from these equations. So let me just show you that. Okay, watch the calculator here for a minute. If I just type in 40 cos 0 plus 25 cos 65. I get this number, right? And similarly, if I just type in 40 sine 0 plus 25 sine 65, I do get this number. Okay, so I've included the analysis here for vector E2 just to try to explain why we're using cosine in the first equation and sine in the second equation. So hopefully you are understanding this fully. Okay, so for vector E1, the full 40 is horizontal, 0 is the vertical. And then for vector E2, this is horizontal and this is vertical according to the diagram. All right, to finish up the question, we use the Pythagorean theorem. So we have to do 50.565 squared plus 22.658 squared. Okay, so let's take care of that now. Okay, so that's equal to ER squared. You can see it's more than 3,079. And now we take the square root of that and we get our value for ER. And we've been asked to round to the nearest tenth in the question. So that will be 55.5 volts. Okay, I think I punched that one in wrong, right? Somewhere, so I'm gonna try it one more time. I believe this should be a 4, okay? Let me just try it once more with you on the display here. Okay, so we have 50.565, 22.658, which I believe I've written down correctly here, but let me just try it on the calculator once more. So 50.565 squared plus 22.658 squared is, okay, so I think that's a little different, 3,070, okay, and that's what we square root. There it is, 55.4 is correct, 55.4. And one thing I just want to point out, so sorry about that error, okay, but one thing I want to point out is even though the question asked me to round to the nearest tenth in my final answer, you can see I kept extra decimal places within my calculation of EX and EY. And this is to make sure that when I round to the nearest tenth, it will be accurate. Okay, there is one final application that I would like to look at with you in this video. And this has to do with sinusoidal current and voltage. So it is true that AC current and voltage do change sinusoidally, and they change according to these equations. So the instantaneous value of voltage can be found by taking the peak or maximum voltage value and multiplying it by the sine of theta. Theta will be the angle of rotation. And here's a similar one for current. So instantaneous current is equal to the maximum current times the sine of theta. So I wanted to show you 4 different problems that could be solved with these formulas. Okay, so we're going to start with example 1. Okay, so let's read the problem and solve it. So it says an AC current has a peak value of 40 amps. So that would be I max. So I've taken the initiative of writing out, as soon as I saw current here, I wrote out this formula here. Okay, and now it says the peak value is 40 amps. So that would be right here in the equation. Determine the instantaneous value of the current to the nearest tenth at 15 degrees. So 15 degrees is the angle. So here's what we do. We start by substituting, again, I max, which is 40 amps. And then we can substitute theta, which is 15 degrees. So the instantaneous current value is just 40 multiplied by the sine of 15 degrees. Okay, there's our answer. We want to round to the 10th, so this will be 10.4 amps. Okay, so that's probably the easiest type of problem because we were solving for the instantaneous value, which was already isolated on the left side of the equation. Okay, so let's try question 2. Question 2 says, an AC voltage wave. So as soon as I saw it said voltage, I wrote down this equation. Okay, so an AC voltage wave has an instantaneous value of 90 volts. So that's here, instantaneous value. So the left side now is 90 volts at 35 degrees, and the angle is 35 degrees. Determine the maximum voltage. So we're going to be solving for this quantity. Okay, so we begin by substituting. On the left side, we substitute the instantaneous voltage value, which is 90 volts. We're solving for E max, which is multiplied by the sine of, in this case, 35 degrees. So the question is, how do we solve for the maximum voltage? Since this is multiplication implied, we do the opposite, which you know is division. So we take the 90 volts and we divide it by the sine of 35 degrees in order to obtain the maximum voltage value. Grab my ruler. Okay, so we're going to take out our calculator now and punch in 90 divided by the sine of 35. There's our answer. And we're going to round to the nearest hundredth. So to 2 decimal places, this is 156.91. So the maximum voltage, or the peak voltage, is 156.91 volts. Okay, so this means that all of the voltage values at all times fall between 156.91 and negative 156.91. Okay, because we're picturing, remember, a sine wave, and this 156.91 represents the amplitude of that sine wave. Just like in question 1, the amplitude of the sine wave was 40. Okay, let's try the next example. Number 3 reads, determine the phase angle. So this time we're going to solve for the angle theta. Determine the phase angle at which an instantaneous voltage of 125 volts appears in a wave with a peak value of 225 volts. Okay, so again, as soon as we see voltage, we make sure we write down this equation here. So that's what I've got so far. Now, we're going to substitute a value here for EI and here for E max. So this is EI. It's the instantaneous voltage, so it goes here. And this peak voltage is also the same as the maximum voltage, so it goes here. And so we still have sine of theta sitting here. So now, how do we manipulate this equation to solve for theta? The first thing you do is isolate sine theta, and that's done by dividing. So you're taking 125 volts and you're dividing it by 225 volts. And that is what gives you the sine of theta. Now notice what's going to happen. The unit volts cancels, see? So you have sine of theta is 125 divided by 225. Okay, if you wanted to punch this number in first, you could. 125 divided by 225 is this number, 0.5 repeated. So now you have the sine of theta is equal to this number. Okay, so you could do that. But the question is, how do you go from sine theta to theta? Well, that's when you know to take the sine inverse. So you're taking the sine inverse of either 125 over 225 or the sine inverse of 0.5 repeated. So let me just show you that, okay? So if you're keeping it as a fraction, then you just do shift sine 125 over 225, and you get this, right? That would be in degrees. And if you've already gone ahead and changed it to 0.5 repeated, then you do shift sine 0. Now you can't just do 0.5. You got to put lots of them, okay? Lots. And then push equals and you'll get the very same angle. And the other way, of course, is shift sine and then a bracket, 125 divided by 225, like that in the bracket, and same angle. Okay, so each and every way we got the same angle. We want to round to the nearest degree. So that means rounding to the nearest 1. So this will be 34 degrees. Like that. Okay, one final problem for today and for our lesson. Example 4. Now, example 4 talks about current. So I've begun by writing out this equation. Now, this one's a little tricky. Let's read it. It says, an AC current has an instantaneous value of 4.5 amps at 16 degrees. Determine the instantaneous current at 55 degrees. So this actually requires 2 different steps. Can you determine what we must find first? If we're given the instantaneous current along with an angle, what can we find first? We can find that maximum current. So that's how we begin, okay? So let's start. We were given the instantaneous value of 4.5 amps, so that's here on the left. We were not given the maximum or peak value, but we were given 16 degrees. So upon substituting, we have this. This allows us to find that peak value by using division. So 4.5 amps divided by the sine of 16 degrees will give us the maximum current value. So let's begin by working that out. So we take 4.5 and divide it by the sine of 16, and this is what we get. We get, 16.326. So that's the amplitude of the graph, or the peak value, if you like. Now, what were we trying to find? Determine the instantaneous current at 55 degrees. So let me rewrite the equation now. So writing the equation again. Here's the equation. What are we trying to find? The instantaneous current. So we're solving for this on the left side here. We're given the number of degrees, 55. And the key to solving this problem is that, of course, you use the same I max value that you just calculated. The peak value has not changed. So here is where you will substitute 16.326 amps. And this time the angle is 55 degrees. Okay, so that was the key to number 4. You had to determine that amplitude or I max value first, then rewrite the equation with that value substituted, and the only difference now is the angle is now 55 degrees. This, of course, is multiplication implied, so we take the 16.326 and multiply by the sine of 55. And here's our answer. We want to round to the 10th, so 13.4 amps. So I hope you understood this last problem. Essentially, what we have is the same peak value, of course, because it's the same sinusoidal wave. And we're just looking at the instantaneous current values at 2 different angles of rotation. The angles of rotation are different, 16 degrees and 55 degrees, and there is an instantaneous current value associated with each of them because you're looking at a different position on the graph. Okay? Okay, so that is the conclusion of the lesson. And what I'd like for you to do is take a look. So in total there are 3 handouts, right? 1, and then 2, and then 3 handouts. And these are all posted for you in Blackboard. At the bottom of each are textbook questions that you should try. Okay, so at the bottom of each page, I have identified which textbook problems would be appropriate. So do take the time to try all of those problems and let me know if you have any questions at all. Okay, thanks so much and have a great day.